This lesson is on simplifying radical expressions. So notice that radicals are really just fractional exponents. We've seen that. So all exponent rules will apply to radicals. In addition to the exponent rules that we have already looked at and that you can review in the exponent rules video, we can notice that roots can split over multiplication and they can split over division. Now, why is that? Is it true? Let's say you had the square root of 36. Well, we know that that's 6 because that's 6 squared. Square root of that is 6. But we also know that 36 could also be written as 9 times 4, which are both perfect squares. And so we could then see that that's the same as going root 9 times root 4, which is 3 times 2. 3 times 2 is equal to 6. So yes, it works to split a root with multiplication. But does it work for division? Well, let's take an example similar to the one we just did. Say root 9 over 4. What times what gives you 9 over 4? Well, 3 halves times 3 halves gives you 9 over 4. But you could also see that that's root 9 over root 4, which is 3 over 2. So that works. However, does it work for addition or subtraction? Well, let's try the same example. Say you had 9 plus 4. Can we then say that that's the same as root 9 plus root 4? So think about that. Here, you'd have 9 plus 4, which is 13, root 13. But here you'd have 3 plus 2, which is 5. Is 5 equal to root 13? Well, if you check on your calculator, the approximation for root 13 is 3.6, nowhere near 5. So you need to really be careful with not using the rules that you normally use for multiplication and division for addition and subtraction. The biggest example that I often see is this one. So say you had the square root of a squared, say this is a plus or minus, so let's say it was a plus, b squared. Is that going to equal then a plus b? So this is a common error that happens. You try it out with numbers just like this, put in a 9 and 4, and convince yourself that it is not true and that you cannot do anything with that. So please beware of things like that. So let's simplify. But what does simplify mean? Well, simplifying a root, a radical, means that you do not want to have any perfect square factors left in the radical. So how do we do that? Well, let's take an example and let's factor it and see what it's composed of. So 160 is made up of 2 times 80, which is 2 times 40, which is 2 times 20, which is 2 times 10, which is 2 times 5. You can do this in any way, and you can see that that is really the same as 2 times 2 times 2 times 2 times 2 times 5. Now you could write that 2 to the power of 5, or you could write it out. Eventually you might start using more exponents. This is x to the 6 and this is y to the 11. You could write out 6 x's and 11 y's. However, how do we look for perfect squares? Well, perfect squares are formed when you have a pair of factors that are the same. That's not a pair. So you can see that this is actually the same as the square root of 4 times the square root of 4 times the square root of 10. Those won't simplify, but these will. And times the square root of x to the 6 times the square root of y to the 11. Now, looking for pairs of factors, you can see that those 2's actually made 2's out of the root, right? 2 times 2 times root 10. The root 10 didn't simplify, that's not a perfect square. But these factors of 4 that were in the 160 simplified. So there's many ways of writing this out. I'm just kind of mapping it out here so you can believe that it is true that you can take those two 2's and make them just 1, 2. That's mostly because that's a square root, so we're looking for pairs of factors to make perfect squares. Now what about the letters? Well, the letters, the same thing goes. If you imagine 6 x's being written out, how many pairs are there? So you can remember that x to the 6 square root is actually the same as x to the 6 over 2. And if you recall from the previous lesson, it was saying that if you have 6, right, then you divide by 2, meaning you look for how many pairs are there. Another way to look at that is to say, well, x to the 6 is the same as x squared cubed. So there's many ways of rewriting these, and basically you're just trying to rewrite them so that it's easiest to simplify. In this case, it's easiest to simplify if you consider it as 3 groups of 2 groups of 3, and you notice that the squares cancel, and that's x cubed. Right, so each of these will come out of a root as 1x, and so that'll be x times x times x, giving you x cubed. Now you don't have to write this out each time, but I'd like you to reason things out rather than memorize rules. So if you imagine the x to the 6 as written out as 6 x's, you can see that there are 3 groups of x. So really you're cutting the exponent in half. That'll be x to the 3. Now this one is 11 y's. So that's not an equal number of 2's, but we can rewrite it as an even exponent, 10, times an odd exponent, 1. And so that splits it so that we see 4 root 10x cubed. These are all multiplied, and now this root y to the 10 can become y to the 5, but this root y is still left. So when you rearrange it so that the roots and the regular factors are organized, you see that that's going to be 4x cubed y to the 5 root 10y. The 10y, that's 2 times 5 times y. Those have no pairs of factors that will simplify. But we had a perfect square of 4, perfect square of x cubed, and a perfect square of y5 that simplified. Now, if you are really good at your multiplication tables, you might have noticed right away that 160 is the same as 16 times 10. So you could have also written it out like this, 16 times 10, knowing that 16 is a perfect square. If you know your perfect squares really well, this can help as well. And you could see that this is 6, and you'd want to write out the y to the 10 times y so that you can take half of those and leave the other one there. So when you rewrite it, you know that the root 16 becomes a 4, root 10 can't do anything, the root x to the 6 is an x cubed, y5, root y, and you have the same thing. So just different ways of mapping it out for yourself, but giving you the same answer. So select the method that you find the most useful, but the goal is to get rid of any perfect square factors. You'll notice that if it's cubed, you're looking for perfect cubes, fourth perfect to the fourths. So we'll see some of those coming up. So doing this, simplifying the perfect square and leaving whatever's not simplifiable inside actually makes it easier to simplify bigger expressions with no loss of accuracy. So in the case of this 10, the root 160 actually became 4 root 10. Now 4 root 10 is the simplest way to write it so that you can combine it with other terms, but it's not losing accuracy because you haven't used a calculator to approximate the decimal value of root 10. So there are cases in mathematics that ask you for exact values, and exact values imply that you leave any roots alone and you don't use your calculator to simplify them into decimals. So let's take a look at some examples here. I'll start with the first one. So I like to imagine each of these as, so this is 9x's written out, this is 21x's, 21y's, and 6 2's. Now a cube root of a negative, we right away know that the negative will come out. With 6 2's, you know that we're looking for groups of 3. So imagine 6 2's, you're looking for groups of 3, there's going to be 2 of them. So this is actually going to come out, that's going to come out as a negative. This will come out as a 2 cubed. And you could also see that as 6 over 3. Remember the division. Two squared, and that's the same as 6 over 3. Remember that division principle, because that's 2 groups of 3 2's each. And again, this is going to come out as x to the 3, because that's 9 over 3. And the 21 also divides by 3, so that'll give us 7. So that's negative 4x cubed y to the 7. Now here, sometimes you need to rewrite it so that it is multiples of 4. So 3 to the 5 can be written as 3 to the 4 times 3, because that's 4 and 1. And then a to the, not 14, because 14 isn't divisible by 4 evenly, but what's the closest thing that is? Well, 12 is, but you need another 2 to make 14. And then b to the 7, well, b to the 7 can be b to the 4 and b to the 3. So I've written them out so that I can take out any quadruplets of the same factor, because I know that those will simplify under the 4th root. The other thing is you never want to forget to write the index, because it'll change your answer if you forget it. So this becomes a 3, 4 over 4. That's left. This will become 12 over 4. So a to the power of 3 groups of 4 a's to make 12. That's left. B to the 4 is just a b, and b cubed was left because that's not enough to come out. So you can see that these come out and these stay in, and I like to organize it like this just so I see everything and it doesn't take up too much room on my page, but you can write it out in any way you like, as long as you end up with a simplified form where there are no perfect factor pieces under the root. Okay, let's try the next one. So the negative's just hanging out front. Remember, the root can split over the top and the bottom. So this is a square root, so we're looking for pairs of factors. So let's write out the factors for 75. Well, that's 3 times 25, which is 5 times 5. So this 5 times 5 can become a 5, and the 3 is left. And here you had how many groups of 2 a's to make 8? So you can also see this as a to the 8 over 2. So that's negative 5 root 3 over a to the 4. And this one here, the 2x is still there, multiplied by cube root of 64, and 64 is 2 times 32, which is 2 times 16, which is 2 times 8, which is 2 times 2 times 2. You could also see that 64 is 2 to the power of 6. But if you wrote them out, you could see that there's 3 2's there and 3 2's there. Those each come out as 1 2 when cube rooted. And in the bottom you have 10x x's. So I would rewrite it as 9x's times 1x, because the x to the 9 will simplify with groups of 3. So this will be 2x. 2x is part of the top because that's over 1. And the two 2's came out, so that's just times 2. There's nothing left. And in here the x cubed came out, 9 over 3. See how I forgot that? That's very important to keep it there. Don't forget it. And cube root of x. So now we need to simplify that a little bit more. So the x over the x cubed, so this is 4. The x over the x cubed will simplify, so there's only x squared left in the denominator. And then you have cube root of x. Now, it's really important to note, and this is coming up in another video, but you never want to have a root in the denominator. So look up the rationalizing denominator video and check it out. So in this case, because there's a cube root, we'd actually want to multiply by a cube root of x squared to top and bottom, because this here will form, and I'll write it over here a little bit clearer. So you've got 4 cube root x squared over x squared, and what happens to this? Why did I choose this? Well, I chose that so that it would cancel the root out, because now that's cube root of x cubed, which simplifies, and that's 4 cube root x squared over x squared times x, which is x cubed. So technically you need it like this, but see the rationalizing denominator video to clarify that for yourself. And here are some more examples to consider. So here you've got x squared, 4th power. So that's x to the 2 over 4, which is x to the 1 over 2, which is actually just a square root of x. And here, 32 is 2 to the power of 5. And if you look at that, that's 2 to the 5 over 10, which is 2 to the 1 over 2, which is just root 2. Now you can notice that this is occurring in these two examples above here. So if you have a factor, you can actually think of it as a simplification, which really it is a simplification. So if you have 10 and 5, that can become 2 and 1. Or if you have 4 and 2, that can become 2 and 1. So because it goes through the fraction simplification process, you can see it directly like that if you like. So finally, we've got this example. So let's put them together first. It was one big cube root, so that's 3 times 9. And 9 is 3 times 3. And then times x to the 4. So that's going to be x to the 5. But 5x is, because we're looking for cubes, let's rewrite it as x cubed and x squared, because that's still 5x's. So that way we see that 3 cubed cube rooted becomes 3, because technically we have this. And this becomes x, because technically we have this. And the cube root of x squared is left inside. So I always underline, if I'm doing it this way, I underline what's left so I don't forget it. It's easy to forget pieces here. So here we've got 3x cube root x squared as the answer. And this last example here, again, let's see what we can do with it. Now they're not the same types of roots. So we can't actually do anything in terms of what we did here, but let's just play around with it and look at the fraction exponent, see if we can do anything. That's a to the 1/3 times a to the 2/5. Well, we actually can, because we know that the exponent rules tell us we can add those exponents. So we just need a common denominator, 1/3 plus 2/5. So get a common denominator, times 5 times 3. So that's 5/15 plus 6/15, which is 11/15. So really, this can be simplified as 15th root of a to the 11. Now, both of these can be answers. It depends on what is asked for. If they're asking for radical representation, that's radical representation. If they're asking for rational representation, then that's rational representation.